This is going to be about transductive and inductive. This is a very important concept when building GNNs, so let's dig into it. First, some definitions. Transductive learning. In the context of GNNs, this means that the validation and test edges are going to be used during the training process. And by that, I mean that they're going to be used for message passing on the graph. If they have labels, we're not going to use the labels for training, but we will use the nodes and edges and their features for message passing. And taking a step back, the goal in this case is not to learn a model that can predict new and unseen cases, but rather it's more like running a process that transfers information about the relationship you have between the training data and labels, but you want to transfer that information to the test data. And for a new node and edge that comes into the graph tomorrow, you're going to have to run the full training and inference process again to generate predictions for these new things. You can't use the model you trained yesterday. Let's give an example of this. So let's say you have a graph of users and transactions in the last 6 months, and some are labeled as fraud and some are legitimate. And you want to use those labeled ones for training, and you want to give risk scores to the population where you don't know the labels. Well, during both training and inference, the graph is going to be the same. And if tomorrow you get a new batch of users, you're going to have to add them to the graph and then rerun this full process. Inductive learning. This is more aligned with what you're going to be used to with a traditional machine learning setup. In the context of graphs, the validation and test edges are going to be hidden during the training process and therefore not used for message passing. And the goal in this case is to learn a model that can predict new and unseen cases. And this might even extend to, for example, making predictions on new graphs entirely, assuming they're from the same domain and task, of course. Some examples might be that you have new molecules. Maybe you've trained a network to predict whether a molecule is toxic or not, or whether it treats a certain disease or not. Well, you might want that to generalize to new molecules that were not observed in the training set. Or more subtly, if you have a social network, which is now modified a month later because you have a lot of new users, this is in some sense a different graph, but it's highly related to the one you were using previously, and you might want your model to generalize given that it's an identical task but a slightly different topology to the graph. For a new node and edge coming into the graph tomorrow, in this case, the model can be used to generate a prediction. An example of this might be that, let's say you have the same graph of users and transactions in the last 6 months, but now you break it into two distinct graphs. One with the first 3 months, which will be used for training, and then the second graph is going to include the full 6 months, but the last 3 are used for validation and test. So the second graph actually includes the first graph, but it has extra stuff, which are the validation and test. Well, during training, the validation and test nodes and edges are not going to be used for message passing, so that's going to be this first kind of subgraph. And then after training, the 3 months will be added onto the graph, and then the model can be used to generate predictions. So that's where the validation and test nodes and edges will be used for message passing to generate these predictions. In the inference, you have a different graph, but the same GNN parameters. And for a new user tomorrow, you just add them to the graph and evaluate with the same model. Another difference that's a little more subtle between these two is that transductive models are a batch processing setup. You could conceivably run it on a single instance, but really it's set up that you have a batch of things, a training set, a test set, and you're transferring this information from one set of data to another set of data. Whereas inductive models can conceivably be thought of as being real-time or individual inference request. This, of course, assumes that you can construct the k-hop neighborhood of a node using something like a graph database, because you're going to need to be able to construct that subgraph to actually evaluate the GNN. But with that complexity aside, you can conceivably, if you have the parameters in the subgraph necessary to create the computation, you can evaluate a single request at a time, whether it's new or old. One of the critical questions you're going to have to answer that's related to this question of transductive and inductive is how you're going to handle nodes that don't have natural features. Let's talk more about this. You have a few options in general. One thing you could do is create features based on the graph structure. So for example, something like the node degree, you could use that as a feature. You could run PageRank and use the PageRank value, or you could count, for example, different motifs like closed triangles of how many closed triangles does a particular node is it involved in, or higher level motifs. Or you could calculate the Laplacian eigenvectors and use the values of those eigenvectors as features. Another thing you can do is just give random values to all of the nodes that are just constant random values. And this seems strange, but it actually works pretty well in practice. And the idea behind this is that nodes that share a lot of the same connections are going to be mapped to similar places when you apply the message passing operation, and that's enough, because if the inputs to the aggregation are the same or close to the same, then the output of that aggregation will be close to the same, which essentially is another way of saying if they share a lot of the same neighbors, they're going to have nearby embeddings, and that might be enough for your problem. And to demonstrate this, I have this little graph here. If you consider A and B, let's say the aggregation we're applying is just an average, and I've assigned random numbers to these each of these nodes. And you see that the computation here is identical. It's averaging the same set of numbers, except in the case of B, it has one more node that it's connected to, which here is labeled as E, and that's this extra 0.11. But all the other numbers in this average are identical. And you can see that the average itself, the answer to these expressions, is very close together. And that's what you would expect, that if the majority of these things are identical, then the output is going to be close together. And that's why even if we assign just random values to all the nodes, that for the ones that are connected to many of the same neighbors, they're going to end up in close proximity in the embedding space. Another thing you could do is have learnable node features. So maybe you randomly assign, but then you make them learnable. And of course, you don't have to just choose one number. You could make this some d-dimensional vector. And these will be learned just like any other parameter in the model with backpropagation and gradient descent. However, the embeddings are only going to receive a gradient if they're in the k-hop neighborhood of a training node. Meaning that if you have a big graph where only some of the nodes are labeled, and then let's say you have a k-layered GNN, if it's your test node and it has these learnable embeddings, there's no gradient on the test node itself because you don't use the label of the test node. So the only way that node will receive a gradient is if it's in the computation graph of a training node, or if it's in the k-hop neighborhood of the training node. Another thing that people do is one-hot encoding, which essentially assigns a unique identity to each of the nodes. But what you see is if you multiply this by a parameter matrix W, you're ultimately going to dedicate a column of W to each node, which is equivalent to just assigning these learnable node features as we just described. So these two things are actually equivalent. Okay, how does this relate back to transductive versus inductive? Well, let me give one example. We mentioned that the learnable embedding passing through this k-layered GNN is only updated if it's in the k-hop neighborhood of a training node. But clearly this means that if the edges for all of the validation and test nodes are absent from the training process, then they'll never be in the k-hop neighborhood of a training node and will never receive gradients for their learnable features, which will mean they have meaningless learnable features. They'll never be updated. Which, another way of saying this is that if you're using learnable features, then you're forcing your model to be transductive, because there's no clear way to assign meaningful values to new nodes that you get coming through the door tomorrow, because they have to participate in this training process to be learned. And this kind of exposes a discrepancy between theory and practice somewhat. For example, sometimes you'll see in the literature that GCN is considered transductive, but GraphSage is marketed as inductive. And in theory, this makes some sense because methods rooted in spectral convolutions, like GCN, are considered transductive because the filters that are learned depend on the spectra of the Laplacian. That's why it's a spectral convolution. And the Laplacian itself will change when you add nodes and edges, and therefore the spectra will change. So the thought is, well, the filters applied to the spectra no longer make sense. The eigenvectors themselves have changed. The spectra are based on that basis. So, how can you apply that to a different graph? There actually is a counterpoint to this argument, and there's a reference at the end for that says that while the spectra may change, the learned filters themselves may actually generalize. But that aside, in practice, the inductive methods like GraphSage are actually identical to GCN. The real difference between these two is that the neighbors are sampled in the case of GraphSage, but nothing about sampling neighbors necessarily makes that inductive, whereas not sampling neighbors makes you transductive. In my experience, the real difference that determines whether your model is transductive or inductive is a consequence of your features. That if you have natural features or you use something like random constants, that can allow your model to be inductive. Whereas if you have learnable features, that clearly puts you in this transductive case, as you're going to require training gradients to get your learnable features. And structurally calculated features are going to depend on how you calculate it. For example, using the node degree is a trivial thing to do. PageRank, however, is a little more complicated. Maybe you could come up with some approximation scheme, but when you add new nodes to the graph, that could perturb the PageRank values of the nodes that were already there, so it gets a little more complicated. The point is that when you're making decisions about node features, you need to think through what the implications are going to be on how you can use the model later. To summarize, in the case of a transductive model, you essentially are going to have a batch processing setup where information from the training data and labels is transferred to the validation and test set, and the validation and test data participates in the message passing operations during the training process. And essentially, you're assuming a static graph between training and evaluation. And one of the advantages is it allows these learnable node features, which can be very powerful. In the inductive case, you potentially have a real-time setup where you can make an inference for a single node that's coming through the door right now. And you have this because you've learned a general model using the data and label from the training setup. And in that case, the validation and test data were withheld from the training process because you're trying to simulate what you're going to do in production, which is you already built your model and now you're applying it to new stuff. And you're assuming that the GNN parameters are fixed and will generalize to either new graphs or perturbed versions of the existing graph. But what this requires is that your node features be obtainable without having to participate in the training process. So you're not going to have learnable node features in the same way that you do in the transductive case, because there's no way to generate that for a new node coming through the door. You need something like natural features or ones that you can calculate based on simple graph things that can just look at the local neighborhood, for example. The reference here is diving in deep to this question of whether spectral filters can be thought of in an inductive setting and not just transductive. So if you'd like to see a more formal treatment of that question, this would be a good place to get started.